Hello there. I am Carrie Sullivan and I'm the Director of Marketing Communications at TechScan. I'd like to start by really thanking everyone for joining us in this session. We're excited to share this information on gait analysis today and really encouraged by the volume of interest that people have shown. So thank you for coming. Gait has many different meanings today. There are different methods between observational and objective. And we hear this all the time, so we decided it was important for us to discuss the methods and also share with you how TechScan's technology fits in. Our speaker today is Marshall Kendall. Marshall's experience is vast. He has advanced degrees in biomechanics and human kinetics. He's done a lot of research, including with sports performance and biomechanics. And he's actually worked with TechScan for over a decade, close to 12 years in the account management role. We're really lucky to have Marshall's expertise on board, and he has a lot to share with you today. So let's get into the session. Marshall is going to start by really talking about and defining gait and the gait cycle, as well as truly the clinical significance. There are various ways to look at gait, as I mentioned earlier, ranging from visual observation to really advanced technologies today. And there are a lot of options, so it's important we really address that. Finally, we'll really emphasize and highlight the type of information you can get from TechScan's technology, as well as the parameters we use and provide for gait analysis.
Welcome, everybody. Today we're going to talk about gait analysis, kind of a part one. For some of you it may be a review, for others it may be some new information, but we're trying to fit it all into about a 35 to 40-minute session here. So let's get started. Some of you may also be clinicians as well, working with patients. So observing the way a person walks, runs, and moves can tell important information about the health of that individual. There are many uses for analyzing the way people move and the way animals move, for that matter. And if we just look at an example in the animal kingdom, if we want to go as coarse as that, to look at and see how hunters actually pick their prey, these hunters will actually use different physical cues such as gait, speed, and balance, asymmetries, to look for weaknesses in their prey to determine which one they're going to attack. So even the simplest of minds, if you will use a form of gait analysis to survive. In more civilized societies such as ours, we tend to use gait analysis for other purposes, such as determining gait health issues, asymmetries that may be associated to specific pathologies, in order to help monitor rehabilitation techniques and to determine proper treatments for optimal health outcomes. So if we look back at the evolution of the idea of gait analysis, there are some key contributors who helped evolve this methodology. The first evidence can be of humans studying locomotion can be seen as early as the Egyptian times, though mostly done through observations using the naked eye. Aristotle provided one of the first accounts of observational gait analysis, describing the way humans and animals walked sometime around 350 before the Common Era, and thus the observational era of gait was essentially born. It wasn't until 1900 years later that the famed figureheads such as Da Vinci, Borelli, and others developed theories and made observations on interactions of muscles, nerves, and their effects on balance in the center of mass displacement. Borelli's research was key to initiate the idea of gait analysis, creating essentially a snowball effect of published papers by a number of important researchers. Leading the way were the Weber brothers, who were the first to observe and measure the stance and swing phases of the gait cycle, leading to the pendulum theory. This theory essentially is the idea of the conservation of energy in the body functioning as a human, as an efficient machine. This group of researchers were a key transition point, deviating from the traditional observational methods of gait analysis towards using more measurement type techniques, bringing about the measurement era of gait analysis, essentially quantifying gait. While research in gait progressed, so did the ability to capture and measure gait. Jules Etienne Maré, working in France, Edouard Muybridge, working in America, made significant advances in measurement technologies, especially in photography and cinematography, which would be today's motion analysis systems. These advances led to the infamous detailed sequence of horses gallop through the use of serial photography. Otto Fischer, in collaboration with Willem Braun, helped make it possible to measure actual ground reaction forces through the development of the first force plate, which today is still considered the gold standard for three-dimensional ground reaction force measurement. The development of these different analysis tools has led to a better understanding of gait and ultimately helped researchers apply these findings to help their patients. Researchers such as Vern Inman and Howard Eberhardt made major advances in gait analysis through the breakdown of the different phases of gait, which led to the creation of a more clinical approach to gait pioneered by David Sutherland, Jacqueline Perry, and Jörg Baumann in Europe. It was not until the advent of modern computers that gait analysis actually became more widely available. So let's look at the meaning of gait and why it's important. Gait is defined as a series of alternating movements of the lower extremities in a rhythmic motion, which results in forward progression of the body with minimal energy expenditure. Why is gait important? It's essentially the means for people to move from place to place, whether that's by walking, running, or skipping. The inability to walk or be mobile can not only affect a person's ability to get from point A to B, but can also create significant health problems over both the short and the long term. Many people can move about with abnormal or asymmetrical gait patterns for many years without any symptoms. However, if a patient becomes symptomatic with pain or has an injury or another type of pathology, normal gait can be altered. If pain, injury, or other pathologies come into play and normal gait is altered, this can cause other problems such as musculoskeletal problems, health issues such as cardiovascular issues due to inactivity, and even affect mental health issues such as loss of independence and depression. Now, pain can affect the way we walk. However, musculoskeletal misalignment over the long term can also lead to overcompensations of the body, which eventually will also lead to pain. So it's important to note that while the pain may not necessarily cause the musculoskeletal problems, the reverse can also be true, where misalignment, bilateral asymmetries can lead to compensatory changes in the body, resulting in pain or injury, which can only be determined or prevented through some sort of investigation of gait analysis. So let's take a look at the gait cycle and break that down essentially. So what we have in the gait cycle is two main phases, which we'll take a look at here. The first phase is the stance phase, and that comprises about 60% of the total gait cycle, and can be defined by the time period that the limb is in contact with the floor or the ground. The second part of the gait cycle is the swing phase, which is approximately 40%, and this occurs essentially when the limb is no longer on the ground; it's in the air, swinging across the body. There are also some subphases within the gait cycle, more specifically the stance phase. The first subphase is called the contact phase, which occurs essentially when the heel contacts the floor on the support limb and ends with the toe off of the swinging limb. This takes about 10% of the total stance phase of gait. This is also known as the heel pivot. The heel pivot is defined as the moment where it's essentially the first point of weight acceptance in the gait cycle and facilitates forward motion. This pivot occurs between the ground and the heel of the foot. The second subphase that we'll look at is called the mid-stance phase. It begins with the toe off of the swinging limb and ends with the heel lift of the support limb, and comprises about 20% of the stance phase. This is also the ankle pivot point of the gait cycle, and this is the ankle pivot. Essentially, its function is to transfer the body's weight from heel to forefoot. The main pivot point for the ankle pivot doesn't actually occur between the foot and the ground. It actually occurs in the ankle joint complex itself. The third subphase that we'll look at is the active propulsive phase, which begins with the heel off of the support limb and ends with the heel contact of the swinging limb. This is approximately the total stance phase. And it also includes the function of the forefoot pivot is essentially to propel the body forward for push-off. The pivot point for this phase is essentially between the ground and the forefoot. The final phase is more of a passive phase. It's called the passive propulsion, 10% of the total stance phase, and begins with heel contact with the swing limb and ends with toe off of the support limb. The weight is already transferred for the most part to the opposite limb, and momentum is mostly doing the work at this point, pulling the stance limb off the ground. So why do we perform a gait analysis? Well, a gait analysis is a functional evaluation of the way the person walks. It provides unique personal movement imprint and evaluates the functional limitations within the gait cycle. ATs, PTs, sports medicine professionals should have a good understanding of normal gait and any asymmetries in order to accurately detect, interpret, and provide corrective treatment plans for their patients, athletes, or other to return to normal, pain-free function. So let's now take a look at the different ways gait analysis can be performed. Gait analysis can be accomplished using a number of different methodologies: observational methods, kinematics, or kinetics. And they are probably all used in some ways, depending on the type of tools you have all together. Now, each of these methodologies have their strengths and weaknesses. Let's take a closer look here at the observational method. Observational methodologies, which are also known as more of a qualitative analysis, in a clinical setting would involve a typical physical evaluation done by a clinician, followed by visual assessment of the patient's gait. Clinicians will use different visual cues to compare asymmetries between the left and the right, looking for overpronation, supination, other types of asymmetries that may occur. They may use their clinical experience to estimate changes in gait speeds, looking at shuffling of the feet, segmental asymmetries such as shoulder or pelvic hike. And to aid their analysis, they may also use video cameras and a stopwatch to help validate their assumptions. Some clinicians might use a checklist with patients in order to get a better understanding of the levels and locations of pain, as well as estimate asymmetries for the different phases of the gait cycle. This method has some limitations, specifically that there are not really any quantitative numbers to compare before and after a treatment. Clinicians will also potentially rely on patient feedback to basically ask them how they feel before and how they feel after to see if pain has subsided. And the observations of one clinician may not be exactly the same as the next clinician, so the perceptual differences may come into play here. Now let's focus a little bit more on the kinetics and the kinematics behind the gait analysis. So kinematics can be broken into two subphases, if you will. there's temporal spatial measurements and the descriptive components. Temporal and spatial parameters include things such as the timing variables, distance variables, and calculations of joint angles. The descriptive components surround more of the determinants of gait. So determinants of gait are key biomechanical parameters required for efficient gait. There are 6 of them: the pelvic rotation, pelvic tilt, optimal knee flexion at stance, foot and ankle motions, knee motions, and lateral pelvic displacements. And these were all established back in 1953 by Saunders et al. Kinetics would be focusing a little bit more on ground reaction forces, power, and torque measurements, just to name a few. So how do we actually measure or obtain some of these kinematic parameters and information? There are numerous instruments available in the market that can be used to quantify this information. Each of these instruments offer their own specialties, if you will, depending on what your needs and what your budgets are and what kind of answers you're looking to get. If we look at accelerometers and IMUs, they're typically used to calculate linear and angular speeds, accelerations, give positions of limb in space and time. Motion analysis systems are high-resolution camera systems that can be used to calculate 3-dimensional joint positions and angles, whether you're looking at ankle, knee, and hip, during the different phases of gait. So this can help you reveal differences in joint angles leading to specific pathologies. EMG, so this is electromyography, can quantify muscle activation patterns, timing of the firings of the muscles, and the amplitudes of these activations to, again, reveal muscle timing and amplitude asymmetries that may be related to a particular pathology. Force plates, which most should know about, provide a 3-dimensional ground reaction force information, which can be applied through inverse dynamics. We can then do calculations at specific joint centers to get a better understanding of a pathology or a Gait's effect on those joint centers. And finally, pressure mapping, which provides a vertical ground reaction force information, but also gives you pressure distribution information under the foot. Typically, these systems are mobile, more mobile than a force plate, that is, and they're actually customizable in size as well, depending on what your needs are, which offer a good flexibility to capture data in different environments and also to capture multiple foot strikes at a time in order to calculate other parameters such as the temporal spatial information as well. So let's take a look at the temporal spatial elements of the kinematics and just take a look at some of the parameters and how they're calculated, what they mean. So we have two main headings that we can look at in the kinematic side, is the temporal and the spatial. And temporal, if we look at that side first, we'd be looking more at stance time, so whether it's single support, double support, swing time, step time, stride time, cadence, and gait speed. Whereas the spatial side, which would be more distances, would be looking at stride length, step width, and foot angle. Let's take a look at the spatial side first. So if we're looking at defining how we calculate or what is a step length, it's defined as the distance between consecutive heel strikes of the right foot followed by the left. So if we highlight that, so here we have our left foot strike, and then we have our right step length here, and essentially in optimal gait, you'd be looking to have symmetrical distances between the left and the right foot. There's nothing optimal to say that 0.5 or half a meter is what you're looking for. It really depends on the height of the individual. So you're really looking at trying to have a symmetrical step length left to right. If we look at stride length, this is defined as the distance between consecutive heel strikes of the same foot. We look at our graph here. Our stride length is from our right foot heel strike all the way to the next right foot heel strike. And in optimal gait, once again, we're not looking at a specific distance. We're looking at symmetry between the left and symmetry and between the right foot in terms of these stride lengths. Step and stride width is defined as the side-to-side distance between the left and the right foot. Again, the distance here is there's nothing to say that you need to be within a certain distance, but it has been shown that a wide width, so the wider the width of this while someone is walking, can be attributed as a high fall risk. So if you think of the elderly who walk, they do not take as if someone is unstable, they will not take as long of a stride, and they'll tend to have a wider stance as well, just as with the fear of falling. So to give themselves a wider base of support. And the toe out angle is defined as the angle from the heel to the hallux relative to the normal gait line. You can see our normal gait line here, and then we have our angle of the toe out angle here. Optimal gait says 7 degrees is optimal for the toe out angle. Again, while 7 degrees could be a target to shoot for, symmetry between the left and the right, again, is what we're looking for typically to bring a patient back to some type of their normal gait. Let's look now at the temporal parameters. So we have step time, which is defined as the interval between heel contact of one foot to the heel contact of the opposite foot. So we can see our right step is here from the heel strike to the next heel strike of the opposite foot. And just to reiterate, and it's a little bit of the same thing, when we're looking at the step time, again, we're talking about asymmetries again. So there's not a specific amount of time that would be defined pathological at this point. We're just looking at a right step time of that would be the same as or close to the left foot step time as optimal. Stride time is the time interval between the heel contact of of one foot to the heel contact of the same foot. And again, stride time, asymmetry between the left and the right is what we're looking for. And swing time is the interval between toe off of one foot to heel contact of the same foot. Okay, so the swing time from the time that this foot is off the ground to the time it hits again. And finally, our stance time is essentially the amount of time that each foot is on the ground. So from the heel strike of the right foot to its toe off. Looking again at symmetry between the times between the left and the right. Okay, so that gives us some idea of the kinematic side. Let's take a look at the kinetic side. So some key measurement parameters when we're looking at the kinetics are the external ground reaction forces, so power, torque, pressure. As I mentioned before, when we're using three-dimensional tools as the force platform, you'll get the three-dimensional ground reaction force, the XYZ, which you can see in this picture. Through inverse dynamics, you can start calculating different forces at the different joint centers. You can also focus a little bit more on center of gravity and the movement of the center of gravity using some motion analysis tools, and the center of force, which is something we can get from the force platforms and the TechScan pressure sensors. So let's take a look at the TechScan's family of gait analysis tools. So there's a number of different tools that are offered by TechScan that can be used in gait analysis. If we look at the mats, they're similar. They offer similar information to force plates. They can analyze single-step or static measurements and provide force versus time information, center of force, trajectory, and of course pressure distribution, which is where it differs slightly from the force plate in offering giving information of where the forces may be concentrated under the foot during the gait cycle. There's walkways, which offer a multi-step force time measurement and pressure. So the nice thing with the walkways versus a mat is you can actually capture the multiple steps, more than one, and then do calculations for spatial temporal information, which we just looked at in the previous slides. And the in-shoe system. So this is a unique system in that the previous two systems are more barefoot tools, which will give you some information on what the patient, what type of pathology the patient might have in a barefoot setting. However, the in-shoe system can give you that same information before a treatment, but then allow you to actually test for it after you've provided a treatment. So it does give you the freedom to collect data in the subject's environment, so whether they're walking, running, or performing another type of activity, and again give you that pre and post analysis. Again, so where these systems excel is really in the plantar pressure distribution information that they provide. So while they provide good vertical force information, they can really then use the calculations and the multiple sensor arrays to be able to really show where the foot forces are concentrated during the different phases of the gait cycle. So let's take a look at some of the software and what it looks like from a standpoint of the analysis. So here we can see an example of some force time curves, and this could be from an F-scan or a walkway system. So you can see the multiple foot strikes, left, right, in the graph here. Now, what we can see from this is we can actually concentrate on the specific phases of the gait cycle. So if we wanted to look at where the toe off is occurring, which would be the forefoot pivot, or the heel contact phase, which would be the heel pivot, we can really isolate these areas by looking at these force time curves. These are the same force time curves that you might see in a force plate as well. However, a force plate, you would only likely see one force time curve at a time, whereas this is either through a walkway or through an in-shoe system, you're able to capture multiple steps. So when we're looking at this information with patients, this is what we would tend to get from a force plate, our double hump curve, and hopefully everyone is familiar with that. The nice thing with the TechScan systems is, while you can look at your double hump curve like this and isolate your heel, ankle, and forefoot pivots, because we're looking at the entire foot and we have an array of sensors under the foot, we're actually able to break down different areas of the foot and isolate each of these pivots. So here we can see that we've actually got a green curve here, which is only focused on the heel portion of the foot to isolate that heel pivot. And then we've got the purple curve here that is really isolating the forefoot portion of the foot, which is essentially the forefoot pivot. So we can really then isolate and take a look at what kind of changes are being applied in specific regions of the foot. And a good example of that is here. We've got an F-scan of the right foot here, and you can see our boxes that are placed. And we've got our curves that are showing up here. that you can see our general red curve, which is the entire forefoot, the entire foot, followed by our green curves and our purple curves that are the isolation points, so our heel and our forefoot. Now the nice thing here is you can see that in our red curve, which is our general or our total force curve of the foot, we don't really see any, well, we see some abnormalities here, but when you break down the foot, you can really look at these curves here and get a good idea of that there's probably something not right in this area of the foot. So you can then really focus in on where is that, on which pivot these ailments are occurring, and then really drive your treatments to that area. I think I focus in a bit more. You can see that typically you'd expect this to go up without any pauses, if you will, that are occurring here. So someone that would be in a healthy position would have the forces that are going up and then come back down. In this case, you can see they go up, they kind of stall here, and then they go back up again. So that's what the tech scans systems are able to show you by being able to break down the foot in different segments and regions. So force and pressure are not the only things that you can evaluate with these systems. We can also highlight, we can also track the center of force through the three pivots of the stance phase. In this case here, we've got information from the F-scan that you can look at the center of force deviation, the center of force excursion of the total foot, and then break it down to the different stance phases as well if you want to really focus in on where the differences are occurring. So we're always comparing left foot to right foot, showing the differences between the two, and then the percentage of difference that you're seeing in there as well. And depending on your clinician's needs, maybe they are only going to be looking at changes that are greater than 10% or greater than 15% to really look at those asymmetries, but that's something that they can use as a tool to guide their treatments. The enhanced in-shoe analysis with the F-scan can provide important before and after treatment information to verify footwear changes, orthotic changes, and other types of treatments. So here's a good example of our left and our right foot and our three box, the boxes, the heel and the forefoot boxes being placed along with our total force. And so you can see our total force is here, and then we've got our left foot and our right foot. So you can start looking at those sub phase. So we've got our heel pivot here and our forefoot here, and then look at where the asymmetries may occur. Even if we just look at this really quickly, we can see that they cross right around here, the forefoot curve and the heel curve. They basically cross at this point, and if we look down here, they cross a little bit more towards the left, so you can already see an asymmetry there. So this is some of the stuff that you can see with the enhanced data analysis. The new next-gen walkway solution is, I think a lot of you are familiar with the Strideway. It's a unique modular product, so which is very nice that you can add different panels to it to make them longer. Again, the walkway provides the force and time and pressure measurement systems that the other systems do, but it also provides the spatial temporal information because we are able to collect all the multiple foot strikes, which you normally can't do essentially with a force plate or even our mobile mat platform. They're single step systems. But so you're able to get all this information, the pressure information, center of force time information, but then on top of that, go and get your temporal spatial information for the different phases of gait, and look at your symmetry table. So obviously in your symmetry table, you're looking at essentially 100% would be perfectly symmetrical, and anything lower than that is asymmetrical. And finally, gait reports are important for both the clinician and the patient alike. So our systems do provide these gait reports, and they can be provided for a single evaluation, or they can be generated for a comparison between two evaluations. If you're looking at before and after orthotic, or if you're looking at a progression in rehab, then you can do a comparison before and after and easily print those off and or save them as a PDF for emailing purposes. So to summarize, TechScan's gait analysis solutions can provide clinicians, whether you're a podiatrist, athletic therapist, chiropodist, or another type of important provider in the healthcare industry, with insights into the gait asymmetries, providing you with actual quantitative information to really evaluate your treatment. The ability to confirm or rebut a diagnosis. So typically, clinicians will do a physical exam and already have an idea of what they're going to be looking for, what type of pathologies this patient may have. But these systems will just provide that extra information, almost like that X-ray to confirm that there is an actual break, a broken bone. It'll also provide concrete information to evaluate how the treatment is working. So if they're progressing in the proper direction, or if there has to be a change to the type of treatment that's being applied. And of course, it will provide these quantitative reports to validate the progress over time. So it not only validates to the clinician, but it will also validate to the patient that they are getting the proper treatment and things are progressing as they had hoped.